Hello, everyone. Welcome to the Knowmads podcast. I'm your co-host, Bhavya.
And I'm your co-host, Prachi.
Imagine walking deep into a dense forest without a map or GPS. Initially, you kind of know where you started, but as you wander further, eventually it's impossible to tell where you came from. Every direction looks the same. That's an analogy for thermalization. The initial state's details get scrambled across all degrees of freedom, and as a result, local observables settle into a stable, time-independent state called the equilibrium state. The fact that macroscopic objects equilibrate with their environments is such a ubiquitous experience that understanding it doesn't seem very interesting, although it is absolutely non-trivial. At equilibrium, these local observables are represented by their thermal expectation values. So if one had access to a map or perhaps a GPS, which just means keeping track of those initial details, such as any non-local correlations or even the entire state, locally thermalization would still occur, but one could easily backtrack to the initial state. Now, in physics, it is quite surprising how systems behave collectively when compared to the behavior of its components. This is known as emergent behavior. We've been taught that evolution of any system should entirely depend on initial conditions, but we see that a lack of initial state dependence is what actually gives a consistent behavior macroscopically. So what we observe is a relationship between thermalization, irreversibility, the second law of thermodynamics, chaos, and ergodicity. Now, moving to the quantum picture, for an isolated quantum many-body system, this becomes even more fascinating because even though the full evolution is unitary and reversible, which means backtracking is guaranteed, locally memory seems to be lost. Then how does this classical behavior emerge from quantum mechanics? In technical terms, how does the time average expectation value of an observable is equal to its thermal expectation value in the long time limit? A key idea to resolve this is the Eigenstate thermalization hypothesis. It says that each non-degenerate energy eigenstate itself can be considered thermal. Their expectation values fluctuate very little between nearby eigenstates provided the local operator acts on a few degrees of freedom. Intuitively, the way to understand this is that a small subsystem of an isolated quantum system acts as if it's in contact with a thermal bath, which is the rest of the system. So in physical large non-integrable systems, thermal behavior emerges without needing a microcanonical or canonical average, and a single eigenstate often suffices. So if this hypothesis is true, and all the details of the initial state are concentrated around some single energy, then our time-averaged expectation value will give the desired microcanonical and canonical averages. Our guest today is Pavan Hosur, a theoretical physicist in the Department of Physics and the Texas Center for Superconductivity at the University of Houston. His research focuses on understanding topological phases of matter, exotic broken symmetry phases, and how to detect them experimentally. He also explores quantum ergodicity, quantum chaos, and more broadly, how concepts from classical statistical mechanics extend into the quantum realm. We're recording this episode in his lovely office and discussing how our complex yet elegant macroscopic world emerges from the quantum laws that govern the microscopic one. Oh, and make sure you make it to the end for a surprise cameo. So let's go.
Pavan Hosur, welcome to the Knowmads podcast.
Thank you.
So, in most physical systems, we see that the most foundational thing is the thermal equilibrium. We often consider it as the natural long time state of any physical system, where macroscopic observables just become time independent. So let us start by you telling us why is it the most foundational thing, and what does it tell us about the dynamics of the physical system?
Well, so those are very deep questions. I'll try my best.
Yeah.
Um, so thermal equilibrium is one reason it's foundational is that, like you said, it is ubiquitous. It happens in almost every system. So it's important to understand why it happens and to be able to describe it well. And that has inspired formulations of physics such as thermodynamics and statistical physics. And what it tells us about the dynamics of the system is, well, so that question can be answered in many different layers. But there is something, I guess the dynamics also, the fact that thermal equilibrium is foundational and fundamental tell us that there is something fundamental about the dynamics as well, which occurs in most systems that exist in the universe at various scales, which evolve towards thermal equilibrium. So that's perhaps a very high level, but a general take on the question that you asked, why is it foundational and what does it tell us about the dynamics? So yeah, hopefully that's a somewhat satisfactory answer.
So like, I mean, but like, again, we can keep it fairly general.
Sure.
The idea is that this time independence of this equilibrium state is essentially boring, right? Because organisms like us humans, we need to be in like this non-equilibrium state to exist. So does all these questions also contribute towards why the thermal state is crucial or the equilibrium state is crucial? Or are there any other features that it has that makes it so fundamental in physical systems?
So yes, so like you pointed out, a lot of the interesting things that happen in the universe are away from equilibrium.
Yeah.
So in that sense, the thermal equilibrium system is boring, and it's a state of high entropy. Maybe we'll touch upon that at some point. Life and organisms are very low entropy states. They are highly organized.
Right.
So it is. What was your question again?
Well, the question was that despite the fact that it is this boring state, why do we still care about it, essentially? That's the crux of the question.
Right. So I think it's because my opinion on it is that it's because it is so ubiquitous. Almost everything reaches thermal equilibrium.
Right.
And it is very hard to avoid it. You have to work very hard for it to not happen.
Okay.
Right.
Okay. So yeah, we can sort of like try to, maybe jump in a little bit. So sometimes these two words, equilibrium and thermalization, are used interchangeably. One is a state, one is a process. Are they synonymous in some context, or are they just fundamentally completely different things? How do you think about it?
So yes, thermalization is a process, and it takes us towards thermal equilibrium.
Okay.
Equilibrium is a broader term. In physics, we also learn about mechanical equilibrium. There is chemical equilibrium in chemical systems. So equilibrium is a broader term, but when we talk about equilibrium in a lot of physics, in quantum physics, for example, the equilibrium we do refer to as thermal equilibrium, and thermalization is the process of evolution towards that equilibrium state. So yeah, thermalization is a statement about the dynamics. Equilibrium is a statement about the state.
I see.
Right.
I see. So this thermal state, as we know, has no memory of its past, as they call it. So I want you to tell us how something like that happens, and how that happens, and why something like that is important to describe a thermal state.
So why it happens is, so to answer that question, so intuitively, almost everything does thermalize and does not have memory of its initial state. That is something we know from experience, and our intuition, the intuition that we develop for physical phenomena or for laws of physics, often are inspired by our experience. So for starters, the question of why does thermal equilibrium, or why does it not have any memory of its initial state, the question itself sounds strange. It is a very interesting and profound question.
Right.
But that question sounds strange because that's what we see all the time.
Right.
But it is profound because there are other laws of physics, quantum mechanics, that I'm sure we'll talk about more, which says that systems cannot lose their memory. So a quantum system that is not supposed to lose its memory still reaches thermal equilibrium. And there, the reason why it reaches equilibrium or seems to reach equilibrium is because the initial information in that system gets lost in the complicated quantum dynamics of the system.
Right.
So a simple example is a cup of coffee, that is a hot cup of coffee kept in this room, will eventually reach room temperature, and that state has no memory of how the coffee was made, or what its initial temperature was. But all that information in principle is still there. If you had a way to measure the exact position and momentum of each molecule, then in principle you can reconstruct the initial state, but that information is stored in such a complicated way that no real experiment can ever decipher that.
Right. So just talking about that example, two other concepts or notions sort of again show up in this case, and that's the concept of irreversibility and the second law of thermodynamics. So how do these two things fit into this whole thermalization picture?
So irreversibility is related to this idea of memory being lost. So in quantum mechanics, time evolution is unitary, which is reversible exactly. But it seems irreversible because the initial information gets scrambled in a very complicated way.
Right.
And it's very hard to recover. So that's the notion of irreversibility. And the second law of thermodynamics, which is the growth of entropy, it is again in classical physics that is taken as a postulate, or it's stated as one of the laws that must hold true all the time. In the quantum context, the entropy that keeps growing, that is analogous to the classical growth of entropy, is the entanglement entropy. So it's a measure of how two different parts of the system talk to each other and how they contain information about one another. So as information spreads and gets more and more complicated, the entanglement entropy, which is a measure of how complicated this information is, keeps increasing. So in classical systems, the classical entropy keeps growing. In this case, it's the entanglement entropy that keeps growing, and it saturates to a certain value beyond which it cannot grow. And it turns out this saturation value exactly matches what you expect in a classical system.
Right.
Interesting.
Right. Another term that comes up when we talk about thermalization is ergodicity. So how about you explain us what is ergodicity and what are ergodic systems?
Sure. So let's start with a classical example.
Yes.
So the ergodicity is an idea that was first formulated in the 19th century in classical systems when thermodynamics and statmech were being developed. And it's the idea that systems, or very complicated systems with a large number of particles, very quickly explore all the phase space that's available to them. So for example, a box of gas, which has gas molecules, suppose you fix the temperature and pressure and some general properties of this gas. Then these particles move around so fast, they collide and move in very complicated ways. And these dynamics happen at such a fast time scale that they explore every possible state that is available to them in a very short amount of time, and time scales that are much shorter than what an experiment can probe. So the basic notion of ergodicity is that physical systems can explore every possible state available to them very quickly. Now in the quantum context, Uh, in the quantum context, there is one state. So okay, let's stick to the classical case for a moment. So because systems can explore many states very quickly, the idea of ensembles was introduced in classical StatMech, which is the notion that instead of thinking about time evolution of the system, you imagine many copies of the same system, each living in a slightly different configuration.
Right.
And all these configurations together form an ensemble. So the ergodic hypothesis that was proposed in the 19th century was that the time average equals the ensemble average, and that's one of the starting points of classical StatMech. So in the quantum context, actually a very similar idea still holds. So now the state of a system is described by a wave function or some vector in this abstract Hilbert space. And there too, the time evolution of this vector is so fast that it explores almost every state that is available to it very quickly. Alternately, if you are in a specific eigenstate of what's called a non-integrable Hamiltonian, so that is a system, the Hamiltonian of a system that is expected to follow StatMech. So that an eigenstate of such a Hamiltonian, and there are more refinements here, you have to be at a certain energy, but all those details aside, an energy eigenstate of that Hamiltonian is in a superposition of many quote unquote simple microstates. So in the quantum context, the idea of ergodicity or time averages being equal to ensemble averages goes a step further. So here a system can explore all these microstates in one time instant without having to actually evolve in time. A single eigenstate can explore all these microstates.
Right.
So that is ergodicity in the quantum context.
You were mentioning in non-integrable systems, so like let's talk about chaos now.
Sure.
In classical systems, chaos is usually defined as the exponential sensitivity to initial conditions, right? Where the phase space, like the small differences in phase space, rapidly grows over time. But in quantum mechanics, we do not have such divergences, right? In Schrodinger equation, it's linear first of all, and then the time is first order. So how would we define chaos in a quantum system?
Yeah, that's a great question, and I'll try and give my best understanding. This
For sure, yeah.
I think the answer will depend a little bit on who you ask and what their background is.
Okay.
So in a quantum context, the basic idea of chaos still holds. So the long time state, or not the long time, the state after a certain amount of time can still be very sensitive to initial conditions. So for example, you start with, pick a state, prepare some state, let it evolve with a non-integrable Hamiltonian, and see what the state becomes after some time. Alternately, evolve it with a slightly different Hamiltonian. So suppose your system has 1,000 particles, and a local Hamiltonian would have of order 1,000 terms, or maybe a few thousand terms. Let's say you change one of these terms.
Okay.
So now this is a new Hamiltonian. Pick the same initial state, let it evolve with time. After some time, you compare the two final states, and you'll find that they have very small overlap.
Right.
So in that sense, or this is one of the ways in which quantum systems too exhibit very high sensitivity to initial conditions. Or instead of changing the Hamiltonian, you could change the initial state a little bit and see what happens at later times. And then the overlap between the two final states could be very small.
Okay.
So that's one way. There are other measures. People use something called the out-of-time ordered correlator, which shows some sort of exponential growth, which is closer to the idea of classical chaos that is inspired by the exponential growth in classical chaos. But the physical picture is basically this. You change something initially in the state or the Hamiltonian. There are other ideas where you apply a perturbation and then remove it, which is another way of making some initial change. Or there are other ideas where you apply the same perturbation but at different times.
Okay.
So these are all different ways of making a small change to the system
Mm-hmm.
and seeing how the final state or some measurable property changes.
Mm-hmm.
Right. So like the lack of this, again, universal or ubiquitous view towards what quantum chaos is that the reason why, like, well, we know that classical chaos has much sharper definitions than quantum chaos has.
Right.
And that's why you mentioned that there's multiple views that exist and people think about it in different ways.
Yes, it is. So quantum chaos is not as precisely defined as classical chaos.
Right.
And in fact, this exponential growth with Lyapunov of exponents, it was that too only occurs in certain systems. It does not occur in all non-integrable systems.
Right.
Okay.
So you need the system to satisfy certain conditions. You need some separation of scales in the system, for example, to see that exponential growth. But in some other systems, that does not happen. And one way to understand that is at least in finite dimensional quantum systems, things are bounded. Your operator has a norm. So if you measure any property of that operator, it can never become bigger than that norm.
Mm-hmm.
So there is only so much room for the exponential growth to keep happening.
I see.
Right.
Okay.
Right.
That's at least one of the ways in which this is quite different from classical chaos. So it has been a subject of discussion for quite a few years now,
Mm-hmm.
which is what is the best way to characterize quantum chaos and what is even the best way to define it. When do you say something is chaotic and something is not?
Right.
I see.
Does it have to be exponential? What about a fast power law?
Oh.
If
Right.
it grows logarithmically, it's probably not chaotic. I think most people would agree that it's not
Mhm.
chaotic.
Mm-hmm.
Mm-hmm.
But if it grows as a very fast power law, at what point do you say
It
is
or
it?
it's not.
Yeah.
So not all non-integrable systems can be defined as chaotic.
Well, so it depends on your definition of
I
chaos.
see. Oh, okay.
Right.
Okay.
Right.
Interesting.
Right.
So non-integrable is better defined, at
Mhm.
least in my opinion.
Mhm.
So non-integrable is better defined, but I feel chaos is not as sharply defined.
Okay. Okay.
That's fair.
So non-integrable is anything that is not integrable, and integrable has, again, it's not as well defined as it is in classical systems,
Right. Right.
but it has a fairly acceptable definition, which is something that can be solved quickly, either analytically or on a
Mhm.
computer. You can solve it in a reasonable amount of time,
Mm-hmm.
Mm-hmm.
and reasonable usually means power law in the number of degrees of freedom.
Mm-hmm.
Right. And that's due to the existence of at least n constants of motion.
Yes.
If the system size is n.
That's right.
I
Mm.
see.
So
I
if
see.
that exists, then you can solve the system quickly. Now, that's not always straightforward because you still have to find a good basis. And there are examples where things look very complicated in one basis, but if you happen to know the right basis,
Mm-hmm.
then the
Right.
solution becomes very easy.
Right. And to know the right basis is actually, I mean, it's not a.
That's not a
straightforward-
that's
yeah,
not
it's not a
a-
straightforward task.
yeah.
necessarily. So again, still talking about chaos. I believe this was 1955 when Eugene Wigner introduced the notion of random matrices to describe what was the energy levels of heavy nuclei. And since then, these random matrix models have become very popular, and they describe a lot of interacting quantum systems, strongly interacting quantum systems, and so on. I believe that, and I think you briefly touched on this, this sort of led to this first, which goes by the BGS conjecture, that any classically chaotic system should have a corresponding quantum system whose energy levels follow the distribution of the distribution of the eigenvalues of a real symmetric random matrix.
Mm-hmm.
So I want you to maybe give like a small overview of why, like, what are these random matrices and why are such models important in this literature or in this side of things?
Sure. So, yeah, like you said, random matrices were discussed in this context in the 1950s. Wigner was one of the pioneers, and people were thinking about nuclei where all the protons and neutrons, every proton interacts with every other proton. Everything is so closely packed together. And the interactions are so complicated that to a good approximation, the Hamiltonian can be assumed to be random. At least that idea works pretty well in nuclear physics.
I see.
Now,
and then there was like at the time there was no notion of QCD, so like they were just trying to use these random matrices to just figure out what the distribution of energy levels is.
Yeah.
Okay.
So in nuclei.
Yeah.
Now, it turns out this idea of random matrices has been very useful in understanding chaotic and thermalizing systems too. And maybe it might be good to develop intuition the following way. So let's ask what makes a system, what makes it easier for a system to thermalize.
Okay.
So suppose you have a system which has many parts. Thermalization is a process of energy exchange. So when different parts of the system exchange energy with one another, eventually they'll reach a common temperature. That's what we call thermal equilibrium. Now, what would facilitate energy exchange? It's interaction between different parts of the system. So if every part interacts with every other part, then they can exchange energy quickly and then reach thermal equilibrium. And that's the idea that, so therefore, intuitively, when there are many interaction terms in the system, when everything is coupled to everything else, it's likely for a system to reach thermal equilibrium. Or that it makes it easy for a system to reach thermal equilibrium. And on the flip side, if there are some barriers, if energy exchange or exchange of some degrees of freedom is blocked, then the system finds it harder to reach thermal equilibrium. So these ideas directly relate to what we call integrable and non-integrable. An integrable system is something that has many conserved quantities. So there are many barriers for exchanging energy or other degrees of freedom, whereas a non-integrable system is one where these barriers do not exist.
Right.
So random matrices were first introduced when people were thinking about nuclei, the new spectrum of energy levels in a nucleus. But because random matrices, by definition, have many interaction terms, they also make it easy for systems to thermalize. So if a system is described by a random Hamiltonian, then it can thermalize quickly. But interestingly, this idea goes much further.
Okay.
And this was, so I guess there is no proof for this, at least not one that I know of, but it works very well. So when a system does not have many conserved quantities, the Hamiltonian may look nothing like a random matrix. It would have, say, a small number of terms, but just the fact that there are no conserved quantities makes the Hamiltonian very hard to solve, and it just so happens that its energy spectrum, looks like that of what you would expect from a random Hamiltonian.
I see.
So this is nature behaving in a very friendly way.
I see.
The system is very hard to solve, but there are some statistical properties that you can derive and check quite easily.
Interesting.
Right. Okay. So talking about not having proofs, let's now finally get to the eigenstate thermalization hypotheses. So some people still consider it as a working hypothesis, while some take it as an established fact. So what are your thoughts on it? And you can start by explaining explicitly what is eigenstate thermalization.
Sure. So the eigenstate thermalization hypothesis, or ETH, is a bridge between quantum and statistical mechanics. So quantum mechanics tells us that time evolution is unitary. The process time evolution is always reversible. No information is lost. But in StatMech, we find that things do reach thermal equilibrium. Although fundamentally everything is described by quantum mechanics, but physical systems do reach thermal equilibrium. And the ETH is one of the ideas out there. It's not the only one, but it's one of the more prominent ideas out there, which form the bridge between these two basic paradigms of physics. So it's stated in different ways. It was first introduced in the 90s by Deutsch, and he introduced the idea, and then Srednicki just a few years later wrote that down as an ansatz, made it a little more formal, and that's the form that people mostly use these days.
Okay.
And the ansatz by Srednicki is a statement about matrix elements of operators.
Okay.
So it tells us that if you have a non-integrable Hamiltonian, and you calculate all its energy eigenstates, which is very hard to do, but suppose you do that formally, and then pick some simple observables, things that you can measure in a lab, and look at the matrix elements of this operator in the basis of these eigenstates. And he proposed that these matrix elements should have a certain structure. So their diagonal elements are order 1, and they have a smooth part. Then there's an exponentially small the off-diagonal elements are exponentially small. The diagonal elements also have exponentially small fluctuations. So this structure of the matrix elements turns out gives us StatMech from quantum mechanics. That means if you look at simple observables, they do evolve with time. They always will keep evolving with time, but they will spend an overwhelmingly large amount of time in the at the value that is predicted by StatMech. And there will be extremely rare fluctuations away from that value. So this is the crux of the ETH.
I see. Okay. So as you mentioned, the idea is to come up with the concept that a quantum system can thermalize, much like any classical or statistical system.
Right.
We know that thermalization in general, and again following from the discussions that we've had, does not generally occur for quantum system because unitary evolution and so on, and definitely not for for a system that has very small number of, let's say, particles or whatever, leading to a small density of states.
Right.
So like, do you mind, again, we're going to dig a little bit deep into this. Do you mind explaining what is the essence of this large and sort of, why do we need a lot of particles in the system to be able to see something like that in a quantum system?
So there are different levels in which I can try answering this. Perhaps the most intuitive one is the fluctuations about equilibrium are statistical. Okay, so what do I mean by that? Suppose you have a small classical system. You're tossing a few coins, and they either land heads or tails. We all know that on average, half the coins should land heads, the other half should land as tails. But if you only toss 5 coins, then there's a very large chance that you'll get, all 5 landing heads, for example. But if you toss, 10,000 coins, roughly half of them will be heads, the other half will be tails. So there is a law of large numbers. There is, so StatMech or statistics in general relies on things being large for the statistics and the other measures, moments, means, variances, these things to make sense. And the same idea holds in quantum mechanics as well. So when you have a very large number of particles, there is a natural scale that can suppress fluctuations. So for example, when systems reach thermal equilibrium, so when they reach thermal, what I mean by that is the system is quantum with a large number of particles, but it's evolving in time. And if you measure a local observable, you will very rarely see fluctuations. And these fluctuations will be, so strictly speaking, there are fluctuations, but they would be so rare that you'll almost certainly never measure it. This rarity of fluctuations is suppressed by this factor of n. So as you have many particles, the fluctuations become rarer and rarer. If you have a few particles, then it's easier for them to deviate from that fluctuation.
I see.
Maybe another way of understanding this is, if you have many particles, then your quantum Hilbert space is very large. So the process of thermalization has close connections with how information spreads in a quantum system. So if your Hilbert space is very large, it's easy. There's a lot more room for your initial information or memory to get lost in that Hilbert space.
Okay.
If you have a small Hilbert space, then the system can explore the whole space, but can still come back to the original state or close to the original state in a reasonable amount of time. So yeah, so these are a couple of different perspectives where a large number of degrees of freedom is necessary for things to appear thermal.
Interesting.
Okay. So these off-diagonal terms in ETH, we need them to be very small, right?
Right.
If it was an integrable system, we kind of expect them to either vanish or be very structured because of the conserved quantities. But these are chaotic systems. And even though these off-diagonal terms are small and random, but they're still non-zero.
Right.
So what makes them small? Like what... and obviously it's not because because of the orthogonal behavior, right? So why are they small, and maybe just give us some intuition about these off-diagonal terms.
So I guess the simplest way to answer why those terms are small or why they have the structure they have is to be able to recover stat-mech.
Okay.
So if you want stat-mech to emerge at long times or in the right conditions, you need these matrix elements to have a certain structure.
Right.
Another way, and this was more of the way Deutsch approached or reformulated the idea of ETH, is so off-diagonal elements represent how one state can transition into another state because when you apply a certain operator to it.
Okay.
So Deutsch's idea was that if you, say, take an integrable system, or this is one way in which it is often talked about, take an integrable system, apply a small perturbation, or you take a non-integrable system, change the Hamiltonian slightly, then things get mixed up very quickly, or they get scrambled. It's very hard to predict which state will become which other state. So let's say you have some chaotic Hamiltonian, and you add a small term for which, or add a term for which you expect ETH to hold. This term could be the perturbation, and this will scramble all your states in a complicated way. But when you're near the middle of the spectrum, each state has many options for which state it can turn into because of this perturbation. So if you have an exponentially large number of terms for each exponentially large number of states in the middle of the spectrum, and each state has, so therefore each state has an exponentially large number of possibilities, then each matrix element has to be similarly exponentially small. So the off-diagonal term, so in short, the off-diagonal term represents the amplitude for transition from one state to another because of an operator.
Right.
And since there's an exponentially large number of possibilities and no possibilities more better or worse than any other, each possibility is exponentially small.
I see. Okay, this is interesting. You also again, part of the discussion was that these ansatz, or like the general statement of ETH, is about how operators behave over time.
Okay.
My question is, are there any conditions on what these operators could be? Because the way I think about it is that, let's say we have an operator which is sort of a function of the Hamiltonian, so it commutes with the Hamiltonian. But let's say this function of the Hamiltonian is some delta like or something not smooth, which I think was part of the assumption that it has to smoothly vary with E, which is the energy. So some poorly behaved function will just violate ETH. And again, when we're thinking about experiments that we do, these observables that we measure need to be local in some sense. So again, the question is, explain to us why these operators need to be local, and what's the notion of locality, and if there are other conditions or constraints on what the form of these operators could look like.
Yeah, so ETH is stated as a theorem or an ansatz or hypothesis that is expected to hold for simple observables. But the meaning of simple is not very well defined. It's usually taken as local.
Okay.
But it does not have to be. For example, in a system of particles, it's often convenient to work in momentum space and think of particle numbers at a certain momentum, which is a very non-local operator, but it is still expected to obey ETH because it is still simple in some sense. So the statement is that ETH holds for simple observables, which is usually local. But there's no proof and there isn't a strict definition either.
Interesting.
So it's sort of, at least for me, this definition is motivated by what we expect from StatMech, or which observables we expect to look thermal.
Right. So that becomes a condition on
Yeah,
what the operators could look
yeah.
like.
What about the conditions on what systems obey ETH? I'm sure, like most isolated quantum systems do obey ETH, but like, are there any conditions, or is there a boundary which defines what are systems that obey ETH?
So the general statement is that a system obeys ETH if it is non-integrable, which means it is not integrable. And integrable systems are those which have many conserved quantities. So if a system has many conserved quantities, then it will not obey ETH. It's not expected to.
Okay.
But this statement is also, there's more nuance to the statement. For example, and you brought up this idea of functions of a Hamiltonian. So conserved quantity is something that commutes with the Hamiltonian.
Right.
In any system, h squared, h cubed, or any function of the Hamiltonian would commute with the Hamiltonian. So strictly speaking, every system has an infinite number of conserved quantities.
Yeah.
But that's not good enough. We need the conserved quantities to also be simple or local or
I see.
accessible in some way. So if you have those conserved quantities, then you can work in the basis of those conserved quantities and solve your problem or Hamiltonian efficiently. So there is now the adjective simple is showing up in several ways. So ETH holds is expected to hold for simple observables in systems which do not have simple conserved quantities.
Okay.
Right. And does this also sort of, I think, about which systems follow ETH? Does this also fall under this weak and strong ETH, that the notion of weak and strong ETH? And if you can talk about that a little bit.
Yeah, I'll have to think about that because I've not thought about this in a while.
Okay.
So I believe the statement of strong ETH, and we can check this later, I believe it's the statement that every eigenstate, so if you take an eigenstate and trace out part of the system, so write down the reduced density matrix of that eigenstate and trace out part of it and look at the remaining density matrix. If it looks thermal, we say that the system obeys ETH. And I believe the statement of strong ETH is that as long as the system you're looking at is less than half of the total system, the system obeys ETH. That's a strong statement. Or to put this another way, it's also the statement that every observable that has support on less than half the system, every single observable that has support on less than half the system obeys ETH.
Okay.
The statement of weak ETH, if I remember this right, is that most observables, I think the condition is still less than half the system, but at least most observables which are not too large obey ETH. And that is not a very strong statement because it turns out even in integrable systems, most observables will follow these statistical rules of smooth diagonal elements, exponentially small fluctuating of diagonal elements.
Right.
So for a system to thermalize and obey ETH, that is reach thermal equilibrium, every observable which is smaller than a certain size, and that size is usually that's believed to be half the system, has to have these statistical properties for the matrix elements.
I see. So as part of this weak ETH, you can also see in integrable systems.
Yes.
I see. Interesting.
Do you think ETH is like a fundamental property of nature, or is it more like an emergent phenomena?
I would say it is fundamental.
Okay.
Well, I think, okay, this is what I'll say. I'll say emergence is fundamental. So
you
they are
cannot fight with that answer. Yeah.
both true.
Yeah. Absolutely.
I see. I mean, basically what I wanted to know, like, is it like the conservation of energy, or is it like the central limit theorem? Where would you keep ETH?
So it's the central limit theorem. It's something that happens when you have a large number of degrees of freedom.
Yes. Okay. Right. Good.
Yeah.
So I think, another discussion that seems to have not been settled is that does thermalization automatically imply ETH? Because as far as I understand, if we can prepare this initial system with some product state of the whole system, and A and B just describing the whole system, it is not guaranteed that A will thermalize for all initial states, unless, of course, ETH holds true. The question is that unless this strong notion of ETH sort of holds true, and all energy eigenstates are thermal. So, what is the role of initial state preparation in all of this in this picture?
So what we expect is that initial states that are... So all this formulation is constructed to help explain why initial states that are preparable in a lab do reach thermal equilibrium. So suppose you found some way to prepare an initial state that is an eigenstate of a non-integrable Hamiltonian. In principle, that can be done. It's very hard, and it's impossible to do for anything more than a few tenths of particles. But suppose you did prepare an energy eigenstate that will never evolve with time. So there won't be any time evolution, nothing will change. So you asked what is the role of initial state preparation. The initial state that is prepared, so all these ideas are developed so as to explain why initial states that can be prepared easily do thermalize. But once these ideas are developed, they apply to a much broader class of initial states too, even those that cannot be prepared easily. There's a very small class of states like energy eigenstates, which are very hard to prepare, and they won't show time evolution, but we don't care about that. So as long as all this formulation works for things that can be prepared in a lab, we say that we are happy, and then don't push that further.
Right.
You were also talking about entanglement entropy, but how can we use it to study ETH when, we cannot write entanglement entropy as just the expectation value of an observable. So how do we use that for ETH?
Yeah, that's a great question. So there have been many formulations of or descriptions of thermalization in quantum systems. ETH is not the only one.
Okay.
In fact, it goes all the way back to the early days of quantum mechanics when Schrödinger and von Neumann, they were bothered by these questions. Quantum mechanics is unitary and reversible, StatMech is irreversible.
Right,
so how do we reconcile the two? And there have been many ideas since then. And ETH does not really try to address the issue of entanglement. It's a statement about observables. And entanglement, like you said, is not something you can measure directly. But there have been related ideas, and one that came out quite recently is called the ergodic bipartition, which is an idea that if you split your system into two parts, then subject to certain constraints like energy conservation, so if you split the system into two parts, then the two subsystems are maximally entangled.
Okay.
and there are constraints, energy conservation, maybe you have some other global conservation laws, and you also have to be at high enough energies. But as long as we are within these conditions, the two parts are maximally entangled. And this can also explain the process of thermalization. So with this assumption, you can think about how things evolve with time, how one part of the system would evolve with time, and look at the time evolution of the density matrix. And it turns out that will still reach the thermal density matrix. It will be very close to the thermal density matrix. But the approach here is different. It's more state-based rather than operator-based. And therefore it directly addresses, and in fact it was inspired by what an entanglement does in thermalizing systems.
Right. So just like as we have this this ansatz for this operator statement, do we also have something like that for this state-based ETH?
Yes. So the basic idea, well, the physical statement is that they're maximally entangled.
I see. Okay.
And once you start with that statement, you can write down, try and express the state on the whole system in terms of eigenstates. So take an eigenstate of the whole system, try and write that as a sum of eigenstates or sum of product of eigenstates on subsystems. And you'll find that these coefficients are essentially random numbers. They're similar to the random numbers that we encounter in ETH. And they have the same exponential structure suppression where needed, so as to reproduce StatMech.
Interesting. So given, again, following from all we've discussed so far, we know that it's hard to prepare isolated quantum systems, and again, even harder to prepare desired initial states. What, according to you, are some of the experimental grounds to test this, and that perhaps are in the near future?
So to test the ETH?
Yeah. And are people already thinking about this? Are they working on this?
So there are many people working on this,
Okay.
In theory, in experiment too. In some sense, the experiment for testing ETH works extremely well because everything we experience in the real world does thermalize. So that's an excellent experiment. The kinds of systems that people try to test this more systematically in is in cold atoms, because there you can control parameters, control the interactions, and also keep the system very well isolated from the environment. So that's the other thing. ETH, at least in its original form, is designed to explain why isolated systems thermalize. So for that, you need to isolate your system from the environment, and that's relatively, or compared to any other system, it's easiest to achieve in cold atoms. Having said that, because the ETH is considered boring, I don't think there are many experiments trying to test the ETH itself. They are trying to test related concepts like the growth of entanglement or growth of or chaos in quantum systems. And there are experiments in cold atoms and in some other contexts too that are exploring these ideas. The ETH is explored most numerically, not so much in experiments. And numerically too, there aren't too many tools. We have exact diagonalization. In some special cases, you can use DMRG or tensor network methods. But tests of ETH mostly occur in numerical experiments, not lab experiments.
So these other lab experiments will probably just have some signature that might tip people off about ETH.
So mostly in these lab experiments, I guess also because lab experiments are much more expensive and harder to develop, the motivation also has to be much stronger. And because ETH is considered boring, there's more effort in trying to find exceptions to ETH. So that makes systems more interesting. In fact, a major line of research for a long time, but especially in the last 15, 20 years or so, has been in trying to find systems which do not satisfy ETH. And there have been experimental efforts to design those experiments in a lab, usually in cold atom systems.
So what's the motivation there? Why would people want ETH to fail?
Because at a very high level, when a law of nature fails, we move forward. That's how we make progress in science or in understanding the universe. We look for failures of our laws.
Right.
And when thermalization does not occur, that's an opportunity for us to understand why thermalization is not occurring in this system when it occurs in almost everything else.
Right.
So that it's, to a good extent, it is curiosity driven. Can we use that for something useful? Maybe there are ideas for, storing. And when ETH fails, that means we don't have memory of we do have memory of the initial state. So if you store quantum information in that state, it will survive for a long time. So there are some ideas for using it in that way.
I see.
But those are still in very early stages as far as lab experiments are concerned. But those are some applications that people talked about. But in my mind, I think it's mostly curiosity driven, that a law of nature that is ubiquitous fails, which makes the system interesting and gives us an opportunity to learn something more.
And even theoretical developments, for example, many body localization. Could you talk a little bit about that? Why is that ETH fails in such systems?
Sure. So many body localization is the idea that if a system is sufficiently disordered, so a system has, so there are two terms there, many body and localization. Many body refers to the fact that there are many particles which interact with one another. And localization is the idea that particles localize. That means if you, say, shoot an electron in from one side, it will not reach the other side.
Right.
It will get stuck somewhere and get localized in that system. So many body localization is one of the best known counter examples to ETH, systems which violate ETH. And since we talked about memory, that may be the best perspective to understand what the difference is. So when a system localizes, it stays there for a long time and it does not exchange energy or particles or other degrees of freedom. For systems to thermalize, they should be able to exchange all these things. And when they do exchange degrees of freedom, they thermalize, they obey ETH. But in a many body localized system, systems get stuck or particles get stuck where they were. They're not able to move around. And therefore, an initial state that was prepared stays like that for a long time. So that's perhaps the most intuitive or visual way in which these systems violate ETH.
I see.
This field, though, has been quite controversial, and I've not followed the latest developments, but what I believe the current status is that MBL is believed to occur in 1D, but not in higher dimensions.
Oh, interesting.
Okay. Yeah, so this is the latest that I've heard.
I see. So again, so one thing is definitely true, ETH is not boring, but apart from answering the very trivial question, which is definitely not trivial, that how statistical mechanics emerges from quantum mechanics, what are some other potential places where ETH comes into the picture and can provide answers to some fundamental questions?
How information propagates in quantum systems is one area. How it propagates, spreads, gets scrambled, that's one area. So another area which is getting a little more attention, and I think it will get much more, is in using that for developing, say, algorithms, classical or quantum.
I see.
So non-integrable systems, by definition, are systems which are very hard to solve exactly. But as we've learned over the years, they do satisfy certain statistical properties. So can we harness those properties to still solve these systems approximately efficiently? So can we develop classical or quantum algorithms which can study non-integrable systems efficiently, and they make use of the fact that these systems have certain statistical properties. So that's one area that has a direct practical use.
I see. So you talked about the current status of MBL, but coming back to ETH, what's happening right now? How has that ansatz evolved? One of the other things we talked about was that now we also have this state-dependent notion of ETH as well. But what's the current development? And if you mind talking about the stuff that's interesting to you and you are looking at right now?
Sure. So there are many different directions. One big area is trying to find exceptions to ETH. So MBL is one example. There are things called quantum scars, which are also another type of exception to ETH. So there's a big effort by various people trying to find exceptions to ETH.
Could you describe what are quantum scars?
So these are states which are still in the middle of a spectrum. The system is non-integrable, but there are some special classes of states which, so if you initialize your system in that state, then it does not thermalize. If you initialize it in some other state, it will thermalize, but there are some special states which are in a non-integrable system. They satisfy other conditions about being at finite energy density, all that stuff, but they still don't thermalize. The orbits keep repeating. The classical analog is periodic orbits, and this is a quantum version of
I see.
classical scars. So that's another class of exceptions. So a different direction is developing quantum algorithms, quantum or classical algorithms. Another direction is trying to make the ETH, understanding it more deeply. So there are several sub-directions within that.
Yeah.
So when Srednicki wrote down his ansatz, although he didn't say it, but people assume that the random numbers are Gaussian. But that assumption turns out to be too strong, and there are non-Gaussian correlations between these random numbers, and there's been quite a bit of development in recent years trying to understand these non-Gaussian correlations. So looking at moments beyond 2, looking at 3, 4, 5 and higher order moments. And exploring that turns out as we've stumbled upon connection to a branch of mathematics called free probability, which is the statistics of non-commuting variables. So that's a branch of math which is fairly new. It's not very old, and it is still developing, but it is more established than it is in the physics community. So it turns out ETH has connections to this branch of math. So that's something worth exploring more, and that's something we've been doing in my group too. That's another direction. Yet another direction is what happens to ETH when there are some conserved quantities, when there is a small number of conserved quantities. So an integrable system is one where there are many conserved quantities, but what you have just one or two or a few conserved quantities, which is quite common in most systems. So we would still classify the system as non-integrable, but how these matrix elements look in the individual sectors of these conserved quantities or between different sectors is unclear. There's been some clarity in recent years, but that's still a direction. Then the interplay between ETH and symmetry breaking. So many systems show spontaneous symmetry breaking. So that means at high energies, the system preserves a certain symmetry. As you cool down, every eigenstate still preserves the symmetry, but the system randomly picks one of the two. For example, a piece of iron is non-magnetic at high temperatures, but as you cool down, it becomes magnetic. It's a ferromagnet. And so when there's a spontaneous symmetry breaking, that means by definition there was a symmetry to start with. And ETH, and if there's a symmetry, then there's a conserved quantity.
Right.
So how does the idea of ETH interplay with these conserved quantities, and what happens if a system has spontaneous symmetry breaking? And depends on the type of symmetry. Is it what happens if the symmetry is some binary symmetry like inversion? What if it's a continuous symmetry like rotational symmetry? What other structure and features within the ETH ansatz develop in all these cases? So that's another active area of research.
That's
Right.
interesting. These quantum stars, does it have anything to do with the Poincaré's recurrence theorem?
I don't know that I don't know enough about quantum scars to
Yeah.
answer that. I believe it's different,
Okay.
but I could be wrong. So let me not say anything at the
Okay.
risk of
Okay.
saying something wrong.
Okay. So let's let's get like a little philosophical.
Okay.
EDH seems to like only like have the entire framework in quantum mechanics. But the good thing or the bad thing is that it doesn't require any wave function collapse, does not require any observer in that sense. So does EDH sit comfortably between different interpretations of quantum mechanics?
I mean, sits comfortably with the way I like to think about quantum mechanics.
This is interesting. Go on. What is it? What
I
how do you
mean,
think?
so I don't usually think about wave function collapse or special observers which can make observations without touching the system. So at the end of the day, the observer is also a quantum object. So everything is interacting with everything else.
Right.
So the process of measurement can be thought of as the observer and the system reaching some sort of equilibrium.
Yeah.
And ETH sits perfectly well with that perspective.
I see.
That's
I see.
very interesting.
So do you think about these foundational questions at all, or sometimes people just end up subscribing to this shut up and calculate sort of philosophy.
Yeah, I'm more on that side.
Okay.
So I do think about foundations of. So ETH is a foundational question, and
Right.
it talks about how things evolve, what happens when there are symmetries, and perhaps the developing algorithms, something I've been thinking about recently, is even more along the lines of shut up and calculate. But yeah, I personally have not thought about deeper philosophical questions such as wave function collapse or
Many worlds and so on.
many worlds, all those interpretations. I think of quantum mechanics as, or at least I don't feel the need to worry about those interpretations, because I think of measurement as simply another interaction.
Okay.
And since everything is quantum, it does not bother me at a philosophical level.
That's
very well said.
put. Okay, so let's move on to the tail end of the podcast.
Okay.
We all of us are interested how people like yourself and other guests that we have on our podcast. How did you initially get interested in doing physics? I know you were part of a family that was predominantly STEM, so maybe also talk about how was that growing up.
Yeah, sure. So I got interested in science from a very young age. My father is a retired chemistry professor, and I grew up in India in a community or in a neighborhood of scientists. So we lived in a colony.
Brilliant. Okay.
And that was mainly for people working at a certain scientific a research institution,
Okay.
Faculty and staff working at that institution. So I was surrounded by scientists from a very young age, and my dad was an inspiration for me in that regard. So I got interested in science from a very young age. For a long time, around high school, I thought I wanted to do chemistry because I was getting better scores in chemistry than in physics. But when it was time for me to choose a major, this was still right after high school. I was starting college, and I was choosing between different majors. The physics description sounded cooler. There were words like black hole and quantum and all this stuff.
Okay.
So that sounded cooler. That had an impression. But perhaps the most, or at that stage, a more concrete influence was this famous book by Stephen Hawking called The Brief History of Time.
Wow.
So I read that when I was in high school, and I learned a fair bit, but I also started thinking about physics somewhat more seriously. So I guess that's how I got into physics at that age, around just after I finished high school.
Interesting. And being around these people who were, again, part of this scientific community, was that helpful? Did you have discussions with them often? And I know your father was an influence. Were they also kind of contributed to that?
So, well, with friends, I guess we were too young to have scientific discussions at that time.
Okay.
But there was still a sense of people, a lot of my friends were still inquisitive. They were curious, and they were intellectually curious. So that trait did affect me as well. And so that's something that had an influence. And I guess that's one of the factors through which curiosity grew. We would, when we played, I must have been 8 or 10 years old, we played usual physical games like soccer and cricket and all those games, but we also had quizzes between us. We played games like that.
Interesting.
And we all nerded out, but that was an influence.
So you said you've always been very close to the academic side of the world, and now you're a professor. So how do you think academia has evolved over all of these years?
So,
or has it evolved? I mean, could be either.
I think it evolves both in time and space. So academia in different countries is very different. I grew up in India. The academic structure there was, the environment was different. The factors that affected major decisions were different. For example, in India, individual people don't apply for funding.
Right.
It comes directly to the institute. I mean, you can apply for individual funding too, but that's not the norm.
Yeah.
So here everything is driven by funding.
Right.
So we have to continuously apply for funding. So that's one difference. With time, I think it's harder to see how it has changed over the period that I've been in academia, which is 15 years or so, give or take. I think it has evolved a little more towards publishing in higher impact journals. In recent years, there's been more weight to that, and also publishing more, writing more papers.
Right.
And I guess,
You think that impacts research?
yes, I think it does, both in positive and negative ways.
Okay.
So there is more pressure to publish in higher impact journals and write more papers. But at the same time, there are more tools now for writing papers, for researching. We can easily find anything on the internet or AI.
Right.
Information is very easy to find. So that has made this process more fast-paced, but at the same time, it has also inspired other tools, inspired AI tools. It has inspired other technology which is useful or used in research. For example, Archive is a website that many people use. It's very old it would still be considered old.
Yeah.
But I think it only started in the 1990s.
Yeah.
Which on an academic time scale is not that old.
Yeah, that's true.
So, and now there are other tools, with large language models. There are people trying to develop tools for understanding a research paper quickly or doing some basic research. So so not only has research benefited from these tools, but it has also helped develop other tools or inspired other tools. So that's one way in which I see the academic environment has changed in time.
Right. How about from the perspective of a graduate student? So just like us, you came to the US as a graduate student, international student. Do you think you think similar changes happen on that from that point of view as well?
So I'm not.
So
Can
like
you
you
rephrase
explained
it?
how generally you've seen this change being part of academia in the last 15 years. But like from the point of view of a graduate student, how do you contrast when you came to the country?
Okay.
How what versus what it is right now?
So I think that is true to a good extent. Information is much easier to find now, which makes things easier, but that also means you need to publish more, publish in higher impact journals, draw better figures, do all those things to get visibility. You have to advertise yourself on social media or in other places. So when I was a grad student, we did, of course, there was internet and we used that a lot. We used archive and read papers on the internet, but we didn't use social media that much. I don't think I've ever advertised a paper on social media, even now, which I probably should change. But
was there a conscious choice, or you were just like never a social media kind of person?
I did use social media when I was still a student, but never for academic purposes.
Okay, I see.
So it was more social or
Right.
you know, things you do with friends.
Okay.
So yeah, so I think there is more pressure now to publish more, write more papers, because there are tools and everyone else is doing that too.
Do you think that's this idea of you as a person in academics and also having a social media has kind of like merged in the current times, and now people don't like separate it and then whoever they are? Because I've seen a lot of physicists be on social media and like be very vocal about what they're working on. Do you think that has become a trend?
It has, yeah. I think it's a fairly recent trend, and I think most people in the community have still not figured out what is the best social media platform for this.
That's true.
So we are still learning, but it is becoming more of a trend. Still learning exactly what to advertise, how best to advertise it. The rules for social media, getting attention on social media are quite different from, well, in some ways they're similar, but in other ways they're different from the way you get attention at a conference or when you write a paper.
Right.
So I think we are still trying to learn that, but that is certainly a growing trend.
Okay. Do you think this is also one of the reasons that it's like harder now to find positions in academia once you pass, like once you get through with your graduate school?
Yeah, I think so. I think that part is getting harder, and that has been a trend for a very long time, since long before any of us were born. I think that's been the trend for decades or maybe even longer.
Okay.
Academic positions have been getting harder and harder to find. Having said that, there are some conscious choices that one can make as well to get a better academic position. That is, stay abreast of what the world is interested in at a certain time. And you can always, or you can try to tailor your interests and your work towards those directions. So for example, in the last decade or so, 10, 15 years, there's been a lot of interest in quantum sciences. So if you can work in that direction or relate your work to that direction and make a convincing case that you know something about quantum sciences, it increases your chances much more. On the other hand, if you work in a field that is that was interesting at one point, such as high temperature superconductors, cuprates, there was a lot of interest in that in the 1980s and 90s. In fact, this building was built because of one of those discoveries. But it's very hard to find a position in that now.
Right.
So it's important to stay aware of what the world is interested in.
Okay.
Right.
Okay.
And that has also always been the case.
Okay.
And I think social media has sort of has contributed towards this even more now, because like you said, the information is not just there, it's also easily accessible. So you better be updated about what's
Right.
going on, and you keep tailoring. Okay, that's very interesting.
Okay. So finally, what advice would you give to young physicists, graduate students who are either in the field or like trying to get into this field? What skills should they develop? Where should they pay attention to? What's your advice for young physicists?
So, I think the first thing is should do what interests you. That should be a big part of what you build your professional career around.
Okay.
It should be interesting to you. That's the best way of maximizing your chances of success. You should be aware of what others are doing too. So not only on social media, but also talk to other people in your lab, people at conferences. So be aware of what others are doing, be generally curious. So what that does is, and one of the things that I see many students struggle with is they can do a calculation or an experiment, but they don't fully understand the significance of what they've done.
Right.
And that is best understood when you talk to people and follow other people's work.
Right.
So
Right.
that puts your work in much better context. You understand the significance and can decide whether that should go to, say, a low impact journal or a high impact journal, make decisions like that. And this is already at graduate school level when you're writing research papers. Some skills are very important to develop. So in the current day and age, you should have good computational skills, whether you're doing theory or experiment. But certainly if you're doing theory, learn some machine learning, learn how to use AI tools. That will make you much more efficient at what you do.
Right.
So these are, I guess, a few things I would say. So build your professional career around things that you enjoy, but also try and tailor it and understand its significance by talking to other people.
Right.
And develop some basic skills, or certainly develop writing skills. I think I didn't mention that. You should be very good at communicating, both in written and oral presentation formats.
Okay.
So that is a very important skill that often does not get that much attention. But that makes a big difference in how you do in your PhD or even as an undergraduate student. It affects your productivity by a huge amount.
Okay.
That is very well put. One thing I want to ask is, you mentioned again quite a few times about these AI tools. So how have you?
I was about to ask the same question.
How have you sort of adapted to all these tools that are now increasingly available to the general public to use? And how do you find yourself using all of this?
I feel like the concept of AI, people have been very polarizing. They either like it and they say, okay, you should use it. Otherwise, like there are other side of people who say, no, we should not be using it in research. So what is your take on that?
So I think you should use it, but with caution.
Right.
So I do use it sometimes to look up some literature, or
Right.
I certainly use it for improving grammar and things like that.
Yeah.
Improving the flow of a paragraph. I use it as a writing tool, but it's also useful for browsing some literature or refining an idea.
Right.
But you should use it with caution because it does make mistakes.
Yeah.
There have been times where I asked it, ChatGPT to list some references and
made
give
it up.
the links, and it made them up or linked it to something completely unrelated.
Yeah, no, that's true. That's true. Yeah, you have to use all of these tools with caution.
Yeah.
But again, you found yourself being you sort of acclimatized, or like just more.
Trying to. I'm not acclimatized yet. I'm still in early days.
I see. Okay. I
But-
think we all are. We're all sort of figuring it out.
Yeah, I guess.
Well, that was great. Thank you so much for doing this.
Thank you
Well,
so much
yeah.
for doing this.
Thank
Thanks
you.
for your
This
time.
was awesome.
Thank you.
Awesome.
And we have a special guest in the podcast.
Finally, he gets daddy.
So, for our listeners and viewers, Professor Hosur has just become a father.
He's maybe a scientist in the making.